So hello, everyone. Let's start today with a new speaker of today, that is Marjorie Galinier. She will speak about the asteroid differentiation thanks to the result of Gaia. And I will leave Mauro to introduce Marjorie. Before everything, I will just remind that the question will be done at the end of the seminar. And for those that are online, just raise their hand or put in the chat your question. So,
thanks, everyone. Just a few words to welcome Marjorie today. So she's a postdoc researcher at IAPS since 2 months now. And she's an astrophysicist with a master's in astronomy, astrophysics, and planetary science. Her main expertise is about the study of small or small bodies through reflector spectroscopy. And in particular, she earned her PhD in September 2024 at the Observatory of the Côte d'Azur, and investigating the possible evidence of differentiation on main belt asteroids, in particular by leveraging on the vast data set of the spectroscopy observation of Gaia. So this will be the subject of the seminar today, so I'll leave the stage to Marjorie.
So hello, everyone. Thanks for being here today. And so I will present what I did during my thesis that is entitled Asteroid Differentiation from Gaia Reflectance Spectroscopy. I worked with Marco Delbo and Laurent Galuccio, and now I'm working with Mauro, Gianrico, and Maria Cristina. So I will first give a brief introduction on small bodies and the Gaia dataset. Then I will present the objectives of my thesis, and I will talk about 2 main projects: the search for differentiation by searching for analogs of a meteorite, and the search for potential olivine-rich bodies in the mainland. Then I will talk briefly about the postdoctoral project. So first, how did asteroids form? Asteroids formed in the protoplanetary disk surrounding the young sun. So when the solar system formed about 4.6 billion years ago, the sun was surrounded by a protoplanetary disk of gas and dust in rotation around the sun. And eventually the dust grains accreted into planetesimals that are kilometer-sized bodies. And these planetesimals are the building blocks of planets, so they are what made the planets. However, not all the planetesimals accreted into planets, and some remained in the system, and they can be studied as today's asteroids. So studying asteroids is a very powerful tool to probe the origin and the evolution of the solar system because they are very primitive material. The planetesimals have different compositions, and some are undifferentiated. So the undifferentiated bodies are made of a matrix of some chondrules that are silicate grains, millimeter-sized silicate grains, and metal grains. However, in the beginning of the solar system, there was a lot of aluminum-26 available, and this radioactive isotope has a very short half-life, and its radioactive decay produces heat. And the heat leads the different elements to melt, and the heavy ones to sink in the middle of the body, which led to differentiation. So differentiated bodies organize into layers of different densities and composition that are an iron-rich core, a silicaceous olivine-rich mantle, and the basaltic crust. So some planetesimals are thought to have differentiated. Today's asteroids are organized into different reservoirs, and during my PhD, I studied the main belt asteroids that are orbiting between Mars and Jupiter. So this is a proper elements plot. So we can see the proper eccentricity and semi-major axis of asteroids. Each gray dot is an asteroid in the main belt. And these elements describe the orbits of the objects, so their distance from the sun and the inclination and eccentricity of their orbit. So what we can see in this plot, first, is that there are gaps in the main belt. And these gaps correspond to mean motion resonances with Jupiter. So the objects that drift into these gaps get eventually ejected from the main belt due to these mean motion resonances. That's why we have gaps. These gaps define several zones in the main belt that are the inner main belt, middle and outer main belts, and the so-called pristine zone. Then what we can also see in this plot is that there are clumps of objects in the main belt. So here I circled some of the clumps. And these clumps correspond to asteroid families. So if we take a planetesimal that we call a parent body, and it gets heavily impacted and catastrophically disrupted, we obtain a group of objects that share similar orbits and that they all come from the same body. And these group of objects are called the asteroid families. They are defined in a dynamical point of view using several methods, such as the graphical clustering methods. And these methods only focus on the dynamical properties of the objects, and they group objects together if they share similar orbits. So this way, many families have been defined in the main belt, and here I highlighted only some of them, so the Flora and Vesta families, and other families in the middle and outer main belts. Now, what about the composition of these bodies? So to do so, we have to probe their composition, and several methods exist, but I use mostly reflectance spectroscopy. So when the sun interacts with the surface of an asteroid, its light gets modified depending on the composition of the asteroid, and we can retrieve the composition of the body by studying this light. So over the past decades, many objects have been observed, and this led to the definition of asteroid taxonomies that are classification of objects. So we can see in this plot the Buzz-Lemire taxonomy, spanning the visible near-infrared wavelength range. And we can see that some asteroids have very flat spectra, and some have wide bands. And this is characteristic of various compositions, such as carbonaceous-rich objects, olivine-rich, pyroxene-rich, and basaltic objects. So this is how we study asteroids. Then if we go back to the families, what has been found by studying the composition of objects in families is that most families are homogeneous, which makes sense since they all come from the same body that was disrupted, but it's also a bit unexpected if we assume that some planetesimals differentiated. We would expect to find families showing different compositions that are the leftovers of this differentiation. So is there any evidence of differentiation in the main belt? First, if we look at the meteorite collection, so all these fragments of bodies that fall on Earth, and most are asteroid fragments, we can see that there are a lot of types of meteorites, and about 8% of them are differentiated. So we find little sign of differentiation, but we find differentiation in the meteorite collection. In the asteroid collection, do we find evidence of core metal-rich objects, olivine-rich objects, and basaltic crust-like objects? We find families of basaltic crust-like asteroids, such as the Vesta family. We find some metallic asteroids, but do we find olivine-rich asteroids? We would expect to find a lot of these because the mantle took a lot of space in the differentiated bodies. So we would expect to find at least about as much as basaltic bodies. First, what is olivine? Olivine is this silicate material that has a very specific spectrum. So it has a white band around 1 micron and high red rise in the near infrared. And if we are to look for these olivine-rich bodies in the main belt, we are looking for A and SA type asteroids that show these bands and this high red rise. And these bodies are thought to have an albedo of about 0.25. So in 2019, Demir et al. Searched for olivine-rich asteroids in the main belt, and they did a near-infrared survey. And what they found is that less than 0.16% of all main belt objects larger than 2 kilometers are A types, which is very little. And they found that these objects are evenly distributed throughout the main belt, and they are no concentration in any asteroid family. So they found only sparse olivine-rich asteroids. But this was in 2019. And since then, the Gaia data set has been released. So Gaia is an astrometric mission that was launched in December 2013. And in 2022, the data release 3 was published, containing more than 60,000 spectra. And these spectra span the visible wavelength range in 16 bands. So here we can see two spectra of the Gaia DR3 dataset of two different asteroids. So Magnia, that is a V-type, we can see the band, and Ceres, that is a C-type. And we can also see that each of the bands were flagged depending on the quality of the band. So bad quality bands were flagged with a 2. And so this is the Gaia DR3 dataset. And the objectives of my thesis was to search for evidence of differentiation exploiting this data. So as a first project, I tried to search for an analog of a meteorite in the main belt population. This meteorite is called Herschel 002, and it belongs to the group of ungrouped achondrites, and it has been qualified as the oldest andesite of the solar system, with an age of about 4.566 million years. This meteorite has a formation mechanism that is consistent with the partial melting of a chondritic source, and it is thought to have formed in the crust of an early accretive and differentiated planetesimal. So this is a differentiated meteorite, and it teaches us that not all planetesimals have basaltic crusts, but some have andesitic crusts. And we wondered, is there evidence of such andesitic asteroids in the main belt today? Barat 2021, which are the first ones who studied this meteorite, acquired different spectra of the meteorite, powder samples and slab samples, and they compared these spectra with the taxonomic N members of the Buzz-de-Mille taxonomy. And they found that this meteorite has a very peculiar spectrum with a small band around 650 nanometer. And this meteorite does not match with the asteroids that we know. But to compare asteroids with meteorites, we need to take into account space weathering. So when an asteroid is in space, it gets impacted by meteorites and by the solar wind ions. And all these phenomena change the surface of the asteroids, which led to modification of the spectrum. However, when the fragment of asteroid falls on Earth, all traces of this space weathering disappear. So we need to somehow take into account the space weathering to connect asteroids with meteorites. And that's why Barat et al. Applied a space weathering model to the powder sample of the meteorite in order to try taking into account the space weathering. But even doing so, they did not find any spectral match of this meteorite in the asteroid population. This was done in 2021, so a year before the Gaia DR3, and we thought, can we find in the DR3 dataset any spectral match of this meteorite? To search for this, we used different methods. So the first method was a curve matching method. We calculated a reduced chi-square between the meteorite spectra and the asteroid spectra. And we visually inspected every spectra that had a small enough reduced chi-square to make the asteroid a potential match to the meteorite. So for example, this asteroid was found by the chi-squared method to be a potential match, and we visually validated that indeed this asteroid is a potential match. We did not take into account the first and last Gaia bands that are often affected by systematic issues. And this asteroid was also found as a potential match, but due to its very low signal-to-noise ratio, we decided not to take into account this asteroid. Then we used the second method, that is the analysis of spectral features. So the spectral features are parameters that express most of the data variability. And here we took into account the slope of the spectrum between 500 and 750 nanometers, and the depth of the band around 1 micron. So we studied all of these parameters for all the Gaia DR3 dataset. And we found that 51 asteroids match the meteorite without space weathering, and 91 with space weathering. all of these objects are located in the inner main belt, mostly. And so they are all close to the flora and Vesta paradis. So these objects are all potential matches, and we find about 0.23% of the DR3 dataset matching the meteorite, which is very little. So these are examples of spectra that we found as potential matches. This asteroid is a potential match to the non-space weathered meteorite, and these two to low and medium space weathering. So this work was published in 2023, but we still needed confirmation that these objects are really matches of the meteorite. So for this, we need near-infrared observations because the visible wavelength range is very small, and we cannot be sure they are matches. So the rest is not published yet, but it's in preparation, and we observed some of the potential matches in the near-infrared. So to do so, we use the SPECT instrument on the IRTF, which is a telescope in Hawaii, and it spans the near-infrared wavelength range. And we observed about 20 asteroids, potential matches of the meteorite. So these are the spectra we obtained. And then we classified these spectra using some online tools, focusing on two different taxonomic schemes, because every taxonomic scheme is a bit different. And we wanted to see if they agreed between each other. And they do agree. So we found 16 V-type asteroids, one A-type, and one S-complex objects. And two objects gave inconclusive results. Their near-infrared spectra are a bit peculiar. So maybe there was a problem during the observations because it doesn't match at all with the visible spectrum. So we did not take these two into consideration. Then we wanted to see, are these objects match with the meteorite or not? And so I used all of these objects, and we considered as well another asteroid known in the literature to have a peculiar spectrum. So this asteroid is 10537, and it has been found by several authors to not completely match with a V-type spectrum, although it has two white bands around 1 and 2 microns. So we can see here it has a band around 650 nanometers, and its first band is a bit shifted compared to the V-type spectrum. So it's likely not a V-type. So the authors hypothesized that it's a mixture of pyroxene and olivine, and that maybe this object comes from the fragment of a partially or completely differentiated body. So we consider this object as in our study, because if we overplot the spectrum of the powder sample of the meteorite, we can see that they both have the same band around 650 nanometers, and they are both shifted compared to the V-type template. So maybe this object is a potential match to this meteorite. To verify this, we studied the diagnostic spectral features of the spectrum. Now we have access to the near-infrared. We can study the position of the first bands around 1 micron and the ratio between the two bands, because these features are thought to be directly related to the mineral composition of bodies. And for bodies with white bands, they are thought to be insensitive to space weather. So we remove the problem of taking into account space weathering and modeling the space weather. So first, we remove the continuum of the spectra to be able to find the center of the band one. And then we calculated the areas of each band using trapezoidal methods in order to calculate the band area ratio. And we did this for all of our observed asteroids, for the peculiar literature asteroid 10537, and for all the end members of thus the Mio taxonomy. So we obtained this plot with the band one center versus band area ratio. And we can see that all the end members of the Mio taxonomy are here. So all of our asteroids that we classified as V-types are indeed close to the V-type spectral template. Our A-type is there, and this object is supposed to be a S-complex. So indeed, when we look at the spectrum and we compare it with the S complex of the MIO, we see that the spectra kind of match, but the observed spectrum is very noisy. And it's also very affected by telluric absorptions around here. So maybe that is why this object does not plot close to the S template. So what we find in the end is that all of the observed asteroids plot far from the meteorite samples. And the object that it plots the closest is 10537. It really is very close to the meteorite grouping in this plot. So, which would mean it's the best match to the meteorite. So in conclusion of this work, no asteroid we observed is a good analog to XL002. So the B types are likely basaltic asteroids, and we can see here that they all plot very close to the Vesta family. So it means they are Vestoids. And there were hypothesized in 2023 by Oskiewicz et al. To be V types. So we confirm 14 of them. Indeed, they are V types. Then we observed one A-type asteroid that is up there, which is nice because we are lacking A-types, so a new A-type. And then we have this asteroid here, 10537, that is in the pristine zone. That is the best potential match to XS002. And in their paper, Moskowitz et al. Say that it might be an isolated fragment from a completely eroded parent body. And Barat et al. About the meteorite say that it's an isolated fragment of a completely eroded parent body. So maybe these two isolated fragments are in fact connected. But what remains to be done is to study if these objects can fall into the resonance, and is this resonance powerful enough to eject them so they can fall on Earth? So there's a whole dynamical part that needs to be done to verify if it's really a match on Earth. And there are other asteroids that show also peculiar spectra, like these two. They also show a shift in the first band, and they do not completely match with the V-type spectrum. And they have been observed by the same authors as 10537. So maybe these objects belong to a new class of objects. Maybe they are andesite asteroids. But we need to study them more. We need to try to search for others like this. And we can use the future Gaia DR3 to do that. But since it's still only the visible wavelength range, we will need to do near-infrared observations to study this class of objects. So that was the first project of my PhD. Then I searched for differentiation by searching for olivine-rich mantle-like asteroids in the main belt. And as a first project, I searched for olivine-rich families. So we wanted to tackle this affirmation in the NEO 2019 that there is no statistically significant concentration of olivine-rich bodies in any asteroid family. To do so, we use the literature. So we use the family catalog of Nesvony 2015. And we took into account asteroids classified from spectroscopic data and photometric data in about 50 articles. So in these articles, we calculated the proportion of asteroids classified as A-type versus the proportion of asteroids classified otherwise. And we defined a threshold of about 10% of A-type to consider the family as potential olivine-rich family. And the best candidate out of this was found to be the family 36256. So this family, what do we know about it in the literature? We know it has 57 members in Nesvony 2015. It has a mean albedo of 0.2, which is consistent with olivine-rich material. And it's located in the pristine zone here, close to the 7.3 mean motion resonance. From the classification, we know that 28 are classified in this family, mostly from photometric data, and they are mostly S-complex objects. We do have some A-types. We have 5 A-types in the literature, one from near-infrared spectroscopy. So this one is a confirmed A-type. 2 from near-infrared photometry, and other 2 from visible photometry. And then if we look at the Gaia datasets, we have 15 spectra of objects in this family, and 8 of them were never classified before, never observed before. So we have new data to study this family. So first, we had the occasion to observe one of these Gaia asteroids in the near infrared using again the IRTF. And this is the spectrum we obtained of 33763. And then we decided to classify all of the Gaia spectra we had, taking into account any additional data we could find. So this near-infrared spectrum, near-infrared spectra in the literature, photometric spectra, anything. So we classified the family members. To do so, we used, again, a reduced chi-square method, comparing these objects with the Bus-de-Mayo taxonomic scheme. And we did not consider the first and last bands of the Gaia dataset as usual, because they are affected by systematics. So for the asteroid we observed, 3373, here are highlighted the A-type spectral template of the Mayo and here the S-type. And so we calculated the chi-square between these objects, and we found that the asteroid we observed is an A-type, so good news. And we did that for all the Gaia objects, and we considered the best 2 taxonomic classes for each object. So what we found is among the 15 spectra, 12 are classified A-type as first or second best class. Some have a high enough SNR, signal-to-noise ratio, above 28, to be trusted as potential A-types. They are highlighted here in red. And the objects that have a Gaia spectrum with a lower signal-to-noise ratio, lower than 21, we can only conclude that they are S complex objects. We cannot be sure they are A. And those that are not classified A, we can also not conclude they are not A. They are really too low signal-to-noise ratio to be conclusive. But we know they are S complex objects. So this is what we have from the Gaia dataset. So in total, we have 4 confirmed A-types from Gaia in the literature. 1 from the NEO-ETA 2019 with the visible near-infrared, the one we observed in the near-infrared, and other 2 from the combination of the Gaia spectra and the photometric near-infrared data. So these 4 are confirmed A-types. So in total, if we take the literature, the Gaia DR3, and our observation, we have 36 family members classified, and 16 are potential A-types, which gives a proportion of 44% of A-types. And the second major class in this family is the S complex. So this family is the first one to show a concentration of potential olivine-rich members. So we did find a family with potentially olivine-rich. Then what about the dynamics of this family? So we know it's in the pristine zone, close to the 7.3 mean motion resonance. And in the outer main belt, very close to the family, there's a big asteroid family, that is the EOS family, which is not an A-type family. But there's a link between these 2. So in 2018, Cyrulis et al. Studied the EOS family, and this is what they found. So first, I need to introduce you one concept, that is the V-shape. So when an asteroid family is disrupted, it is disrupted into fragments of different sizes, and each of the fragments are affected by the Yarkovsky effect, which is a non-gravitational effect that leads every member of the family to drift in semi-major axis. And the smaller the asteroid, the faster it drifts. And so we end up with families that show a V-shape in the magnitude versus semi-major axis plot. And we can see here the V-shape of the EOS family. And what Cyrulis found is that in the pristine zone, there's a group of objects that follow perfectly the V-shape of EOS. And they identify these objects as EOS fugitives, that are EOS family members that jumped the resonance and went in the pristine zone. So what about our family? If we look again at this V-shape of EOS and we plot in the pristine zone our family here, we can see that part of these objects follow the EOS V-shape. So these objects are likely to be EOS fugitives. And the objects that are down the V-shape of EOS were all found A-type by our analysis. So it's possible that the 36256 family defined by dynamical methods is a mix of EOS fugitives and an A-type family. So what we can conclude from and also, according to Marjorie 2015, if a resonance is weak and asteroids are small and drift fast in semi-major axis, then they can jump the resonance, and it leads to a discontinuity in eccentricity, which is what we observe here. But the inclination of the objects is not very affected by this resonance crossing. So Nesvorny concluded that the family 36256 was implanted in the pristine zone. And this participates to the fact that some of these objects are likely EOS family members that jump the resonance. So in conclusion, we have all of our potential A-types are outside of the V-shape of EOS. So these objects likely come from one single olivine-rich object that got disrupted here. And maybe the dynamical family is a mix of EOS fugitives and A-types. So these A-types, where do they come from? So if the family, the small family outside the V-shape of EOS, is made purely of A-types, maybe it comes from a differentiated planetesimal, so a fragment of the mantle, that was implanted in the pristine zone and then disrupted there. If this family is made both of A-types and S-complex objects, S-complex that are linked to undifferentiated material, maybe this family comes from the disruption of a partially differentiated body with a layer of chondritic crust and a mantle of olivine. Maybe it also comes from nebular processes, but I don't know if nebular processes can produce a big chunk of olivine. And so the perspectives are to do observations in the near-infrared to confirm that all our potential A-types are A-types. So this is for this work that was published in 2024. And then I continued my study of A-types by studying the full Gaia DR3 dataset and not focusing only on the families. And the goal here was to tackle the other two affirmation of the MIO 2019, that there is less than 0.16% of all main belt objects larger than 2 kilometers that are A, and that they are evenly distributed throughout the main belt. To do so, I needed to classify the DR3 dataset. But this dataset shows some peculiarities that distinguish it from ground-based observation. So we cannot directly compare with ground-based spectra and with ground-based taxonomies derived from the ground-based spectra. So first, I filtered the DR3. I did not consider all the bands as usual. I did not consider any spectrum with flat bands in the wavelength range I was interested in. And I did not consider objects with a low signal-to-noise ratio. So this led me to have only 18,000 spectra. So I kept only 31% of the dataset to do this study, heavy filtering. And then I classified these 18,000 spectra in the bus scheme that spans the visible wavelength range only. However, I tried to directly compare Gaia DR3 spectra with the bus templates, and it gave me non-satisfactory results. So I defined some Gaia templates corresponding to each of the bus taxonomic class. And we can see here some of the classes. So we can see that the bus versus the Gaia templates show some differences above 750 microns. So it's important to compare Gaia with Gaia to do this classification. And then I built a classification algorithm adapted for the DR3. So I classified all of my 18,000 spectra, and I obtained 98 potential A-types. So these 98 potential A-types correspond to about 0.52% of the dataset. And if I take into account only the objects with a diameter above 2 kilometers, I still find 0.5% of the dataset. So these objects, if we consider all the A-types found from spectroscopy in the literature, plus those found from the GR3, we end up with 157 A-types. And we can see in the main belt that they are quite evenly distributed with a slightly larger concentration in the inner main belt. And if we look at the clumps, we can see here a small clump in the pristine zone, and this is the family 36256. So we find again the family 36256 as potentially full of A-type. So to conclude, comparing with the Leo et al. 2019, we find that they found that less than 0.16% were A-types, and we found more than 0.5%, so still a lot more, even if it remains very few objects. And then among our 98 potential A-types, we actually have already 17 that are confirmed from the literature and from observations by Christa Abdelou, so the paper is in preparation. So 73 are left to be characterized in the near infrared and were never characterized with spectroscopy before the Gaia DR3. So Gaia brought something to this study. And then they are indeed rather evenly distributed throughout the main belts. So this we agree. And there's still a lot of things to do. Yeah, so there's a slightly larger concentration of A-types in the inner main belt. And I need to now study this more to know if there is a high concentration in any family and do they really belong to families or not. So this is still a work in progress. So to conclude, the conclusions of my thesis were that there is little evidence of differentiation in the main belt still, even with the Gaia DR3. So there are possible analogs of Hertzsprung 002 in the main belt. Maybe there's a new class of andesitic bodies that was not found before. Then we found that the family 36256 is the first one showing a concentration of olivine-rich bodies. So it's the first A-type family, and maybe comes from a fully or partially differentiated body. And then we find more than 0.5% of potential A-types in the main belt. So we increase the amount of potential A-types in the main belt, and this needs to be studied. So to conclude about Gaia, since it's a large data set and very homogeneous, even if it's different from ground-based spectra, it's powerful to characterize asteroids. And then what is left to be done is a lot of things. So we need to confirm everything with the near infrared. We need to exploit the Gaia DR3 to study the main belt as a whole. So for example, taking into account the new catalog of families of Nesvorny, and search for more differentiated families in this catalog. We need to search for more asteroids spectrally similar to the meteorite, and study also the diversity within, for example, the S complex, because the S complex is a very large complex, and it's possible that some asteroids characterized as S are in fact rich in olivine, but this olivine is not visible. So we need to study this. And also, as I am part of the Gaia consortium, I have to help define a new taxonomic scheme for the DR4. So all of this is left to be done. And now what I do during this postdoc, so I stayed in the spectroscopy of small bodies, but I moved to certain moons. So right now I'm using Cassini data to do compositional maps of Dione, Rhea, and Enceladus. So this is where I am right now, trying to do maps, still room for improvement. And then this will lead me to do spectral modeling of the moons. So I will learn modeling. This I have never done before. And this will help me because in the context of the Eagle mission, I need to support activities to define the near-infrared imaging spectrometers. So I need to try different spectrometers. That's why I need to model the moons. And I'm also involved in the EMA mission that will do the flyby of 6 asteroids. So I guess I will do things also related to this. So that's it.
Thanks, Marjorie, for the seminar. Very nice work. So time for the question. I will leave before the question is in the room. If anyone have question from online, just raise the hand or put the question in the chat. So questions from the room? Go, Valentina.
I have a very stupid question because I'm not an asteroid person, but I always had this question in mind. So we know that the oldest age of the solar system comes from an achondrite. And I don't know if it's the same achondrite you showed before, but I think it's still an achondrite. So my question has always been, why don't we get the oldest age of the solar system from chondrites?
So we get the oldest age because in chondrites, there are calcium aluminum inclusions that are the first solids to solidify in the beginning of the solar system. And so these calcium aluminum inclusion are those who give the age of the solar system.
Okay, so it's not possible to get the
The age of the solar, yeah, because I think the first solids were chondrites. So these calcium aluminum inclusions that are in chondrites.
Thank you, sorry. I always had this buzzer in mind.
I guess also a stupid question, but in the asteroid belt, because your first part was talking about Halloween, but is there like hydrated, is there aqueous altered olivine there?
There is aqueous alteration. So we know that CH type, the H stands for hydrated. So they are the small bands that shows that they are hydrated. I also know in the meteorite collection, we find some hydration. There's like several types given how hydrated they are. So we have proof of hydration. I don't know about hydrated olivine, this I don't know.
Well, because if you had a graph
Mhm.
earlier on, I don't know, I can just,
Yeah.
it's not a critique of you, I'm just curious.
No problem.
Okay, it was like a spectral
This?
of olivine, maybe a little further.
This?
It was like,
Okay.
Yeah, this,
but it was your results, actually was maybe,
Okay.
it was I don't want to waste too much time. It's not this though. It's a different graph.
Ah, it's a different
Yeah,
graph.
it's
Okay.
your real results or some kind of collection of like a bunch of Halloween. No, okay, back before the purple and green,
This
the V shape, yeah.
or
So at 1.9 and 2.1, around 2.0, the
Mhm.
wave form kind of gets sporadic. Is that absorption? Oh, okay.
sorry. Yeah, okay. Where?
In part A, so
Yeah.
in this like around 2.0,
Yeah, here? Yes.
is that like a air or is that like, is that some kind of like weird reflection or is
It's
that?
telluric absorptions. It's the fact that we observe from the Earth and the atmosphere.
So that's
with the spectra here and here.
okay. So that's water absorption from the Earth.
From the
atmosphere?
Earth, yeah.
Ah.
Mm.
Wow.
Mm.
Okay, sorry.
No problem.
That's pretty neat.
Yes.
Very nice talk. I have a question about the exploitation of Gaia dataset, since you are involved in also mission. You are showing spectral indicators computed on a normalized spectra, but what
Yes.
about the absolute value? I mean, try to use in the classification also the real albedo of the spectra and I don't know, colors particular, which could be, I mean, the obvious quantities to be used to further explore the data set.
There's a postdoc in Nice called Alexei Sergeyev, and he transformed the Gaia dataset into colors to do that, to classify Gaia. So that's what he did. He transformed everything into colors, and its classification system works pretty well. So yeah, but here I tried to keep the spectra. The photometry, going to photometry is quite efficient, especially given that we have only 12 exploitable bands in the DR3 dataset, so it's not so much.
So in the future, you can try also to merge the photometric part with the spectral part together. No?
Yes, yeah.
No, I'm asking because many of the spectral quantities we have shown have a clear dependence on the illumination condition,
Yes.
phase angle in particular, which is something which maybe could further improve your classification methods.
The problem of the DR3 is that it's only mean spectra,
Mhm.
so we lose the phase angle
For the single observation.
of the single observation. So maybe for the DR4, we could produce the mean spectra so that the phase angle is taken into account in the procedure already. But I don't know if that's being done right now, but that would be nice to take the phase angle into account. I think most observations of Gaia are like in the 30 degrees of phase angle range, most of them, but probably some are not. So I don't know if they are filtered out or corrected, if I don't know.
A simple question, but I come from a completely different field. But I'm curious, since you're talking about infrared observation of, that you take from ground, and since you're also using the Gaia datasets, I'm not sure if you're aware that there is also a mission that is ongoing, is FAIR-X, that will observe between 0.8 and 5 micron. So in the infrared will be a coarse spectrophotometric survey. But if your targets are not too faint, and since this will be an all-sky survey, possible since the data are already being published, maybe it's worth to check if your asteroids can be in this data product. What I know is that they do not deliver the entire data process for the entire data set. But if you have a target, you can contact people in Caltech at IAPS to try to extract the fluxes, and you can build up then your spectral energy down to 5 micron without the
thermic absorption.
Yeah, exactly. So if this will help your analysis, I would suggest you to have a look at that.
Yeah, I didn't know about this service, so yes, it sounds interesting.
It's a course. It's very coarse, either in spectral range, but also in spatial resolution. It's like 6 or 7 spatial resolution. But I think it's all sky and will be deep. So even if your target is not, it's faint, it is possible that there will be this data.
Thank you. I will look into this. What's the name for it?
FAIR-X.
FAIR-X, okay. Okay.
Sphere.
FAIR-X. Okay.
Yeah, but the main objective of this survey will go for the spectral feature of water and CO in galaxies and in stars. But actually, there will be a lot of product. I'm aware that there are people that are interested in asteroid classification, but it's not my field. So.
Well, Gaia was also built to study the stars. So we happen to have asteroid data, but really the telescope was made for stars. So that's why the asteroid data are less good.
I know, but my understanding of your work is that the infrared wavelengths are more important for the classification.
Completely.
And Gaia is more optical.
Yeah.
So I would say.
Yeah, it's worth investigating. Thank you.
There is a couple of questions online from Jules Bordwell from The Wire. He's asking about the classification of potential asteroid linked with the HAG 002. Have you considered their albedo, especially using MarkTax? Have you also considered the other result given by MarkTax as is statistical tax? You should have other matching. And then the second one, that is with the p-type, have you tried to estimate the age of this A-type family? If yes, what was it?
So for the first question, I did not. So I know the Mark taxonomy, but when I classified the objects we observed, we find an agreement between the different taxonomies. And I think since this taxonomy was built on all the available data in the literature before Gaia, it will not have a class specifically for these weird V-types. So probably in this taxonomic system, it uses statistical belonging to classes, and probably these objects belong to the V type, even if they are strange V types. So I don't think we would find this a grouping, but I should ask Max. And for the second question, it was about the V shape of the family. So the problem is our small family, it's very small. It's here. So if we take into account only these objects, we cannot really make a V type of these objects. They're really, really small. So we cannot deduce any age of this family. Maybe if there are more objects belonging to this family that were not taken into account in the definition by Nesborny, maybe we will be able to bring a V-type method to find the age, but not on these small amount of objects. We cannot do that, unfortunately. So
Each magnitude, is that distance?
the H magnitude is the absolute magnitude, which is the magnitude of the objects if we remove any geometric parameters, so not the phase angle, etc. So it's the magnitude of the object if we were to see it as a zero phase angle. Yeah, the absolute magnitude.
It is just to say that when the magnitude is larger, means these fragments are smaller
Yes.
and they are driven away
Yeah,
by the
by the Yarkovsky effect.
Yeah.
Yes, also.
The size, what, I don't understand.
So the absolute magnitude is the same, like is goes with the inverse of the diameter. So the smaller the object, the fainter it is, and so objects that are very small are more faint.
So it's
And,
it's, okay, that's what you're talking about. So it's a magnitude of light that you observe from it?
yeah.
So it's based on the light angle and the size between.
Yes, yeah. I think I have a slide in the back somewhere. The Yarkovsky effect, so it's related to the inverse of the diameter,
Oh, yeah.
which is also related to the magnitude.
So particles that drift around, they're getting ejected from this main, this larger thing.
Yeah.
But should I be visualizing like a cloud, like a spherical cloud around this thing, or is this a directional?
So I guess it depends on the impact.
Yeah.
And I doubt it's completely spherical. But when there's a catastrophic collision, some objects fall back on the main body and some start drifting away in some directions. And also it depends on their rotation direction. So if their spin on, like if their rotation is on one direction, they will drift towards higher semi-major axis. And if they rotate in the other direction, they drift towards smaller semi-major axis. That's why we end up with a V shape, depending on the spin of the asteroid.
You mentioned early in the talk that the andesitic asteroids are in the inner belt. And I was wondering if that's a function of what you're talking about here, like andesitic objects preferentially breaking up there, or if it has to do with the density or something like that, and that's why they cluster.
So the problem is the objects we found as potential analogs were all in the inner main belt, but most of them end up to, in fact, not be andesitic, and they are probably most vestoids, so linked to the Vesta family. That's why they are here. So the best potential analog is actually in the pristine zone, so in the exterior of the main belt. But I have no idea why it would be here more than somewhere else. So yeah, it's a good question. I don't know.
That's one. Paul, with your last answer about the online question is still asking, in that case, how can it be a family?
So
It was related to the low number.
so the families, since originally they are defined in dynamical point of views, then we use the V-shape to also study the families, but I don't think they are defined taking into consideration this V-shape. And I think it can be like the point of an asteroid family is it's a main object that breaks up. And so if all of these small objects sharing similar orbits are all the same taxonomic type, I think it can be considered a family because they come from the breakup of the main body. Even if we cannot run the V-shape method on them because it's too small. So I still think it's a family.
Any other questions? No. So I think we can thanks again Marjorie for the very